quick little problems here. First, because we can see that this is an equilateral triangle, we see the sides are all marked with the single hash indicating that they are all equal. We know that the regular angles here, like this one, have to be 60 degrees because all the sides are equal, all the angles are equal. So each angle has to be 1/3 of 180 degrees or 60 degrees. An equilateral triangle will always have 60-degree angles. So angle ABC over here is just one of those angles from the original equilateral triangle, so it's 60 degrees. Angle ACD, well, from yesterday we learned that if we have an angle bisector, which is what AC is, from even just an isosceles triangle, but from the vertex between two equal sides, it will do two other things. It'll make a right angle with the opposite side. In other words, it's an altitude. And it will cut that opposite side into two equal pieces. In other words, it's a median. So angle ACD is a right angle, or 90 degrees. And angle CAB up here is half of that original angle DAB, or 30 degrees. Definition of angle bisector is it cuts the angle in half. And finally, segment CB down here, this length, if this is 8, that means all the other sides are 8 because it's equilateral. So CB is half of that, or 4 inches. So the biggest part of that is just understanding the drawing and what everything means, and then putting it together from there. It's not a whole lot of calculation, really. It's just simply remembering the properties of equilateral triangles and what those angle bisectors, medians, and altitudes do to that triangle. So for today, I have to grab my papers here. We are continuing along this line, looking at congruent triangles or equal triangles. Congruent triangles are triangles that are equal in every way. What does that mean? Well, every triangle has 6 pieces. It has 3 angles and 3 sides. So congruent triangles have the same 3 angles and the same 3 sides. Now, it might be a different orientation. It could be flipped over or rotated, but they have the same 3 angles, same 3 sides. However, they might be differently arranged. Prove that triangles are congruent. If we know they're similar, and the ratio of sides is 1:1, then they're congruent. But remember, what did it mean to be similar? Similar meant that they had all 3 same angles. All 3 angles the same. And remember, we said because we know that the angles of a triangle add up to 180, if we knew that 2 of them were the same, we knew the third one had to be the same. We really only need 2 angles. Show that the ratio of sides is 1:1. All we need to show is that at least one pair of corresponding sides now remember, corresponding sides are the sides that are between the same angles, are equal. If that pair of corresponding sides have the same size or same length, well, then the ratio is 1:1. And so the ratio of all the other corresponding sides must also be 1:1. So let's look at combinations. The absolute fewest that we can have is 3 out of the 6 things. Well, let's take a look. We talked about all 3 angles. I know all 3 angles are the same. I can draw a triangle like that with those 3 angles. I could also draw a triangle like that with the exact same 3 angles. Those are not equal or congruent triangles. They are similar. If all 3 angles are the same, we know the triangles have to be similar, but they're not necessarily congruent or equal. So what if we know 2 angles and 1 side? Well, there's going to be a few possibilities here. What if we know a side, then the next angle, and the angle after that? So what does that mean? So that means I have this side length. I know this angle. I know this side. I know that angle. Then I know this next angle. Is it possible to construct a triangle that's different? Well, the first side has to be the same. This angle has to be the same. Well, if 2 of the 3 angles are the same, the third one also has to be the same. So this one here would also have to be the same. And there's only one way I can put that angle in there to get it to come up and meet the other side. So no, if I have a side and 2 other angles, there is only one possible triangle I can create. So yes, those are equivalent, or that word is congruent. What if we had an angle, actually 2 angles, and the side in between them? So I have this side here that must be equal, and I have this angle and this angle. Well, again, if I try to draw that, I have this side that's equal to that. Draw an angle over here that's equivalent to this one, and an angle over here that's equivalent to that one. Oh, those sides have to intersect in the same way. So any combination of 2 angles and 1 side, if I know they're the same, triangles are congruent. And again, realistically, if I know 2 angles, I know all 3 angles. So really, I know 4 pieces. I have a bonus piece when I give that information. So let's look at the different way. What if I know 2 sides and 1 angle? Well, I'm going to start off with the possibility I have the side, 2 sides, and the angle that's in between them. So I have this side and this side, and I know that angle. Well, all I can really do here is close off this opposite side. If I repeat that, I have this side, this angle, and this side. Well, there's absolutely no way that can form a different triangle. So those are congruent. The one that gets a little fuzzy for people is if I have 2 sides that are the same and an angle that's not in between them. Well, people think, well, that still shouldn't matter, should it? Well, let's say I have this side here. I have this angle, and I have this side over here. I can draw a couple of different triangles that are similar to that. Oops, I drew that very poorly. Let me try that again. This side like this. I can actually draw another triangle that's very similar to that. You might think, well, if I draw that first side the same I draw this angle the same. This side length has to go here, doesn't it? Well, no, not necessarily. I can have a side, since this side could be longer or shorter, I can have a side that's the exact same length here that goes over here. So there's two possible triangles formed. That only is possible as if the side that is next to the angle is longer than that second side given. Then that second side can either be tucked in to make an obtuse angle here, or it can be pushed out to make an acute angle out there. So two sides in an angle don't work. We have to have the angle in between them, or we have to have all three sides. So this does not tell us nothing. Not necessarily. Equal or congruent or even similar for that matter. This type of relationship, this possibility here, causes problems all along throughout trig. When we get to our laws of sines and laws of cosines, we're going to run into an issue with this as well. So keep that in mind, that when we have two sides in the angle that is not in between them, there is always two possibilities for what that triangle could look like. And finally, if we have all three sides, this one's pretty obvious, then they do have to be congruent. There's no way you can draw the three sides and arrange it differently so it's a different triangle. It's still, at the very worst, is going to be just a reflection or the triangle flipped over. So in application, being able to tell if triangles are equal, we've seen it a little bit already, is very important. In our trusses, because we knew these two sides were equal, we were able to cut this down through the middle, if that's a right angle, and we were able to tell that those two triangles were equal. So we were able to say if this was a 40-foot span, we were able to determine that this was 20 feet. And the reason we were able to do that, now we just assumed we could do it, but the reason we were able to do it is because this side was equal to itself, these two sides were equal, and we had that angle. But we said, well, wait a second, we have two sides and then the angle that's not in between them. Didn't we say that was the one case that didn't work? Well, it works because this is a right angle. It's like when we know two angles, we know the third one. If there's a right angle, if we know it's a right triangle, if we know two sides, we know the third one. So for this, and also, by the way, we knew that these two angles were the same. So we had two out of the three angles rather than just one. We know those are congruent triangles. We've been focusing on triangles so far, but there are larger mathematical figures. They're called polygons. Polygon's just any figure with straight sides. Or with line segments for sides, I should say. So there's no curved surfaces or curved sides on it. Now we have convex polygons, where all of the interior angles are smaller than 180 degrees. Which implies we could also have something called a concave polygon. Looks something like this, where here we have one interior, at least one interior angle, It is larger than 180 degrees. In construction, we stick usually with convex, pretty exclusively with convex polygons, and also usually with something not just convex, what is called a regular polygon. In a regular polygon, all sides are equal, in other words, it's equilateral, and all angles are equal. A lot of special qualities about those that we will go over. We'll look at our definition again of angle sums here in a little bit. But for right now, let's talk about our different polygons. In any polygon, the number of sides is going to equal the number of angles. For example, if it had 3 sides or three angles, that's what we've been working with. It's a triangle. If it has 4 sides and 4 angles, called a quadrilateral. Now, we've looked at a lot of special quadrilaterals. We've looked at rectangles. We've looked at squares. We've looked at parallelograms. We've looked at trapezoids. But a quadrilateral can be any figure with 4 sides. That would be a quadrilateral. Obviously, there's no special name for that one. It has 5 sides. It's called a pentagon. Notice that ending gon, the suffix gon, that's why these are called polygons. Gon is that standard suffix just saying pentagon means, the gon means sides and angles. So pentagon means 5 sides and 5 angles. 6, of course, is hexagon. Again, hexa meaning 6, 6 sides, 6 angles. 7, there are actually 2 different names for this, septagon or heptagon. Both septa and hepta stand for 7, depending on which root language you're using. 8 is octagon. 9 sides is nonagon. And is decagon. We can keep going from there, but in construction, typically, the ones that are used the most, obviously absolute most, is the 4-sided quadrilaterals. 99% of what we do in construction is a rectangle. The triangles get used quite a bit, and I'm going to come back and I'll mention why the triangles are so important in just a second. But then if we do any special features like turrets or gazebos or anything like that, hexagons and octagons tend to be what we go with because of the regular angles they have. And we'll look at the angles formed in each of those in just a minute. So I mentioned triangles being important to construction. Let's talk about that for a minute. The importance of triangles is simply that triangle is the only shape that is a rigid frame. If you think about it, if I have a piece of wood here, I'm just going to drill a hole in each end. And I'm going to take 2 other pieces of wood with holes in their ends, and I'm just going to put these together with pegs in those holes. Nothing keeping them from spinning. Individually, they can rotate on each other. But as soon as I stick that 3rd peg in there, this is rigid. It cannot move. I cannot move this either direction at all. It will not move. It's rigid because moving any of those joints would require one of the pieces to either shrink or stretch. If I have four sides, however, so I have a bottom piece again, and I'm going to put another piece on it, again with holes in each end. Another piece, I don't want to do it quite like that. Another piece here with holes in each end. But a piece across there. Now, if I push here, I can actually make that fold down. That process of folding down like that has a name. It's called racking. Now, in construction, I said we primarily use rectangles for things. And that is very true. And it's very unfortunate. When we frame a wall, pretend those didn't get really fat for some reason. Of course, we will have a double top plate. We throw in our studs here. Will be a little short. Even though that is studded perfectly according to code, all of the shapes formed here are rectangles. And because they're rectangles, they're subject to racking. The only shape that is not subject to racking is a triangle. So what do you do once you set that wall to keep it from racking? Like I said, it could actually tip. The whole works. Every stud could tip on you like this. How do we keep it from doing that? Well, you nail a board on it at an angle like that, or you nail through the bottom plate and you nail into each stud as the board goes past. What does that board do? Well, it is forming a small triangle here, a bigger triangle here, and a bigger triangle here. That board that we put on there to brace it is forming triangles to make it rigid. Well, we take that board off before we're done. What goes in its place? Well, we put in our sheeting. And the nails in the sheeting form those triangles. So the sheeting on the outside of a house, you think of it as just covering the outside. It's not. It is actually providing a large portion of the structure. The studs themselves are simply providing lift. They're able to support weight straight up along their axis. But they are subject to two defects. One is this racking, and the other is bending. If that stud's only 1.5 inches wide, it could bend like this. It has, in engineering, we call it a low slenderness ratio. It's very narrow, very slender compared to its length, and so the force applied to it can cause it to bend or bow like that. The sheeting holds it in place. Now, if we just have sheeting on one side, that usually does the trick, but a large amount of force can cause, if we look at them from the top, sheeting nailed into it. If we have a large enough force, these studs here can still twist within the wall, and the inside can buckle. It can actually buckle inward rather than side to side because of the ability of those studs to twist. So that is why it is recommended that you put, no matter what the purpose of the wall is, it is highly recommended that you put some sort of interior sheeting on it as well. This doesn't completely stop it from doing that twisting thing with the studs and bowing in, but what it does is it makes it so that every stud has to twist. So it spreads out whatever stress amongst all the studs. And then, of course, at some point there's going to be a corner in the wall. That sheeting pushes up against the corner of the wall, and hopefully that stops it from being able to twist at all. So, again, the point being is those triangles are very important. As we said, when you nail the sheeting on, the nails in the sheeting form several triangles that give that wall its rigidity so it cannot rack and deform. He mentioned angles in the hexagons and octagons being important. Let's talk about the angle sum. We went over this a little bit yesterday. We know that the angle sum of any figure is equal to the number of sides or the number of angles times 180 degrees and then minus 360 degrees. So for a four-sided figure, this would be 4 times 180 minus 360, which is 720 minus 360, or 360 degrees. The interior angle sum of a four-sided figure is 360 degrees. Well, that makes sense. Our common four-sided figure that we use is a rectangle. It has four 90-degree angles. Well, 90, 90, 90, and 90 add up to 360 degrees. If we have a five-sided figure, it's 5 times 180 minus 360. Well, 5 times 180 is 900. Minus 360 is 540 degrees. The interior angle sum of a five-sided figure will be 540 degrees. So if this is a regular pentagon, well, it's regular. That's actually not bad. Regular pentagon, of course, means all the angles are the same, so that 540 degrees would be divided by 5 angles. It'd be 108 degrees per angle. Every interior angle in that pentagon is 108 degrees. They're all the same. If it's a six-sided figure, this is our hexagon. 6 times 180 divided by 360. Well, 6 times 180 is 1,080. Minus 360 gives us 720 degrees. So a hexagon has 720 degree interior angle sum. Well, let's look at a regular hexagon. That's not perfect, but it'll do. It has 6 interior angles, and if it's regular, they're all the same. Well, the sides will be the same as well. We divide that by 6, that gives us 120 degree angles. So each of those interior angles in a hexagon is 120 degrees. Why is this a big deal, 120 degrees? Well, because if I extend one of the sides, if this interior angle is 120 degrees, this exterior angle, those two have to add up to 180 because it makes a straight line. That exterior angle would have to be 60 degrees. And 60-degree angles are actually relatively easy to construct and measure out. If I am making a hexagon with a certain length side, I can use that 60 degrees to drastically simplify how I do it. For example, let's say here is my side here. I want this to be 8 feet. And I want to make a 60-degree turn here and have another 8-foot side. This turn is 60 degrees. In other words, the interior angle, this is a regular hexagon, that interior angle is 120. Well, if I go out here exactly 16 feet, exactly double the length of the side I want, I can measure back here at a right angle, and that will hit that 8-foot side. So in order to make this 60-degree angle, I just go straight out here 16 feet, and I go this way 8 feet, and I adjust that 8 foot until it forms a right angle with a right triangle with that 16-foot side. Allows me to construct that 60-degree angle very simply. There are also some tricks. If we get time at the end of the semester, I'll show you There are also some tricks for using the framing square to make a 60-degree angle. Actually, both 60 and 30-degree angles. We're going to skip the 7-sided figure. We're going to jump up to the 8-sided. Now, the formula we've been using here would say that this is 8 times 180 minus 360. We offered you a shorter version of that formula yesterday. Because 360 is just 2 times 180, instead of n times 180 minus 360, we can subtract the 360 from the n before we multiply. And again, 360 is just 2 180, so it can just be n minus 2 times 180. It makes it a little simpler to subtract the 2 from the n first before we multiply it out. Now in this case, that 8-sided figure, n minus 2 will be 8 minus 2, so it'll be 6 times 180 is 1,080 degrees. So the interior angle sum of an octagon is 1,080 degrees. So if I divide that by 8, that ends up being 135 degrees. Each of these interior angles is 135 degrees. Now again, that might not seem too significant, but the significance again comes with the exterior angle. This exterior angle would be the supplement of 135 degrees, which is 45 degrees. 45 degrees is half of a right angle. So that makes it relatively easy to do. If I want to find a 45-degree angle, I will just measure a certain distance down one side. I can construct a right angle rather easily if I want my 45-degree angle to go this way. I will measure that exact same distance down the other side of the right angle. I will measure across and find the halfway point. Wherever the halfway point is, that's where that 45-degree angle has to go through. So it's relatively easy to construct a 45-degree angle just by bisecting, to use the technical term, by cutting a 90-degree angle in half. Okay, so those different polygons, as we say, have different purposes. We are going to find, in the second half of the course, we are going to look at finding the areas of regular polygons using our trig functions to help us do it. Because their areas are actually not simple to find. One of the rules for the area of a regular polygon let's look at a hexagon here. This is a regular hexagon. One of the methods for finding the area of a regular polygon, so hexagon n equals 6 sides, is I cut it into basically pi wedges. So from the center of that polygon to the vertices, I make a triangle. This is going to be an isosceles triangle. These two lengths are going to be the same. If I find the area of that triangle, I can just multiply it by the number of sides. 6 sides, there's going to be 6 of those triangles. Well, to find the area of that triangle, I would need to know this distance here. That distance has a technical name. I'm not going to write it down because you don't need to know it. It's called an apothem. No, I'm not talking with a lisp. It's apothem. I'll write it down, I guess. Again, you don't need to know that term, but it's that distance from the center of the polygon out to the side. It's also the altitude of one of those triangles. So the area of the triangle is that apothem times the side divided by 2. And then, of course, we'd multiply by the number of sides. The area is if the side length is S, is the apothem times the side divided by 2, because it's a triangle, times the number of sides. That formula, again, we're not going to use it because right now we don't have a good strategy to find the apothem. But once we get into the trig, we'll be able to find it rather easily. That strategy is vital for using trig to find the area of a regular polygon. So when you start talking about regular polygons, the next step is talking about circles. Adam likes to bring up calculus and integrals. Not going to make you do calculus and integrals, but kind of along the lines of calculus, if you take a polygon to the point of having an infinite number of sides, as our polygon has more and more sides, the angles in that polygon get bigger and bigger, those internal angles. They get closer and closer. I didn't do a very good job there. We get closer and closer to 180 degrees, and the sides can get shorter and shorter. Well, as we get more and more sides, it basically becomes a circle as we get up to an infinite number of sides. So the circle is the next logical extension of a polygon. In a polygon, there are parts that we already know about. One is, of course, the center, one of the two defining parts of a circle. First one is the center, the location of the center. That just tells us where the circle is. The second one is the radius. That is the distance from the center out to the circle itself, the surface of the circle. I'm going to find another piece that we haven't talked about much yet, but is very important. It's a line segment that has its end points on the circle, or a line segment that connects 2 points on the circle, and that is called a chord. So a chord is any segment that connects 2 points that are on the circle. Well, now another part that we have commonly talked about is just actually a special type of chord. A chord that contains the center of the circle is called a diameter. Another piece we've talked about quite a bit is just the distance around the circle, called the circumference. Now there are some relationships here. We know if we use d for diameter, that the diameter is equal to 2 times the radius. Pretty simple from the drawing, you can see that that has to be. We've seen that the circumference is equal to pi times the diameter, because pi is just defined to be that ratio between the circumference and the diameter. Or circumference equals, since the diameter can be 2 times the radius, 2 times pi times the radius. And of course, we found that big A for area of a circle is simply pi times radius squared. Now again, that pi times radius squared, if we go back to this formula, I showed you one way that we could drive that formula last fall when we saw it. This idea of using an apothem. Also, so the apothem would just be the length of the radius. It also fits into that pi times radius squared idea. There are some other features of a circle that are less common that we haven't talked about yet. Let's talk about some of those right now. One such one is a line that just touches the circle. All the points of this line are outside the circle except for the one point that touches it. And that is called a tangent. It contains no points inside the circle and exactly one point on the circle. All the other points are outside the circle. But the more convenient way to think about it is it just touches the circle without ever going inside of it. a line that contains points both inside and outside. So it could look like that. It could start inside and go outside, or it could actually cut all the way through, start outside, go inside, and then come back out. That's called a secant. Again, a secant is just defined to be any line that contains points that are both inside and outside of the circle. One that we actually did see last semester is this idea here of a central angle. That central angle defines portions of the circle. It cuts the circle into pieces. If I call that central angle theta, looks like this, looks like a O with kind of a line across it. That's the Greek letter theta. It's a variable that is often used. It's when we look at variables for angles, unknown angles, rather than using our Arabic letters, A, B, C, D, E, F, G, whatever, we tend to go to the Greek alphabet. We use theta, phi, alpha, beta. Pi is actually a letter from the Greek alphabet. So here we would have this portion of the circumference of the circle that is cut by that central angle is called an arc. And remember, last semester we had a formula for arc length. It was equal to the circumference of the circle times that central angle over 360. And this pi wedge that is cut out by that central angle is called a sector. And we had a formula for sector area as well. It was the area of the whole circle, once again, times pi over 360. Because that pi over 360 is just what fraction of the full circle each of those portions is taking out. That central angle cuts out, in other words. We could also have a chord on our circle like this. The area between the chord and the outer edge of the circle, that area there, is called a segment. The area of a segment, a lot more difficult to find. We struggled with it a little bit last semester. It was equal to the whole sector area. So for that segment, it would be that sector that we would find the area of minus the triangle area. What triangle area am I talking about? Well, this triangle in here, that's the part of that sector that is not in the segment. If I cut this segment off the outside edge out here, that triangle is what's left over. Now, last semester we did that because I gave you the length of that chord, and we knew the radius of the circle. And we could find the area of a triangle from the three sides. In the next couple of weeks, we'll look at how can we find the area of a triangle if I know two sides, in other words, the radius, and the angle in between them, which is going to be our central angle. We can find the area of that triangle using trigonometry. We have our central angle here. And I'm going to call that angle theta. There are other angles we could have. An angle that has its vertex on the circle is called an inscribed angle. Now, because it intersects the same arc as our central angle, this angle right here is going to be half of this angle. Theta divided by 2. Another type of angle we can form is if we have two secants that intersect outside the circle, that is called a secant angle. Sometimes called an exterior angle. You could have two chords that intersect inside the circle like this. That is referred to as an interior angle. It goes along with the secants intersecting exterior outside the circle. There are special relationships formed here. Obviously, this angle and this angle are the same. And these two angles are the same because those chords are basically just intersecting lines. And our final special angle we could have is if I have a tangent and a chord that has one endpoint at that point of tangency. That is referred to as a tangent angle. Now, it has its vertex on the circle, just like an inscribed angle. So what makes the tangent angle different from the inscribed angle? The inscribed angle, both sides of the angle are inside the triangle. In the tangent angle, one side's inside the triangle, but the other side is exterior, is outside the triangle. It's tangent. Reason we're spending so much time here talking about circles is because we're going to introduce something called the unit circle. The unit circle is a circle with a radius equal to 1 unit. What unit? Doesn't matter. So there's our circle, and we're going to put it on a rectangular coordinate system here, XY coordinate system. But what we're going to do is we're going to label this 0 degrees here, going in the right direction. Just like when we talked about rays and defining angles and the direction of a ray, remember we said the east direction was 0 degrees, and we went around counterclockwise, 90 degrees, 180 degrees, 270 degrees, and of course 360 degrees to be back at 0. So our angles wrap around here going counterclockwise. This would be a 60-degree angle. Well, if we look at those angles, 0 is referred to as the initial side. The ending piece here, in this case where the 60-degree ended, that is referred to as the terminal side. So you think of these angles as almost a rotation. We start at the 0 degrees and we rotate to that ending side or terminal side. That's what's called terminal. We start at the initial side, we end at the terminal side in rotation. Well, this arc here is the intercepted arc for that angle. The length of that arc, since this is a unit circle, since the radius of this is always going to be 1 unit, the length of that arc has a direct relationship to the size of the angle. In fact, we can measure an angle by the length of that intercepted arc on the unit circle. And this is referred to as radian measure. So let's start off with the whole works here. If I am going all the way around this circle, that is 360 degrees. If this circle has a radius of 1 unit, the circumference of that circle is 2 times pi times 1, or just 2 times pi. So the radian measure of that angle, being 360 degrees, would just be 2 pi radians. So we have that equivalency that 360 degrees equals 2 pi radians. Well, we can convert other angles into radians by using that equivalency. Remember when we did other measurement conversions last semester? If I had 198 rods and I wanted to convert it into feet, that's not a conversion we know off the top of our head. So we took 198 rods and we put it over 1. Then we use a conversion factor. We put rods on bottom, feet on top. 1 rod is 16.5 feet. The rods cancel out. This is telling us we take 198 times 16.5. And we get 3,267 feet over 1. So that's just 3,267 feet. Well, we use the same type of thing here. Let's say that we have an angle. Well, let's go back to our 60 degrees. We have an angle of 60 degrees. I want to convert that into radians. Well, 60 degrees. We'll make that into a fraction by putting it as 60 degrees over 1. And in my conversion factor, I'm put degrees on bottom. Well, I know 360 degrees equals 2 pi radians. RAD is the abbreviation for radian. So the degrees cancel out here. 60 times 2 pi is 120 pi radians. 1 times 360 is 360. And now what I do is I simplify the numbers excluding the pi. 120 over 360. Both of those can actually divide by 120. I realize you're probably dividing by 10 and then 3 or whatever. Eventually you get down, that is 1/3. So this angle here reduces, the 120 over 360 reduces to 1/3. And then we have the pi and the radians added on to that. Let's do some conversions. Do a couple, and then I'll have you try a couple. Now let's do 225 degrees into radians. Oh, I'm going to set up my 225 over 1. (360 degrees on bottom, so the degrees cancel out. 2 pi radians on top, so the degrees cancel out. Now on top, I have 225 times 2 pi radians. So I'm going to do 225 times 2 is 450. And I still have the pi and the radians there. Notice I don't do much with the pi and the radians. I work with the numbers and just kind of let the pi and the radians sit there. On bottom, I have 360. I'm going to take the 450 over 360, and I'm going to reduce them. Both of those can actually divide by 90, giving me 5 over 4. So this is 5 over 4. I'm not going to put that into a mixed number. I'm going to leave it as an improper fraction. Times pi times radians. So 5/4 pi radians is what that becomes in radians. You know what, so I'm going to have you try a couple. I'm going to have you convert. For one, I'm going to have you do 30 degrees to radians. And the second one I'm going to have you do, let's have you do 135 degrees into radians. I'll give you a minute, and then we'll go over those. Let's take a look at the first one here. You've got 30 degrees. So I put it as 30 over 1, 30 degrees over 1. I'm put degrees on bottom and radians on top so I can convert. 360 degrees is equal to 2 pi radians. So the degrees will cancel out. 30 times 2 is 60, and we still have the pi radians there. 1 times 360 is 360. Well, you can probably reduce this without having to pull it out. 60 and 360 both divide by 60. Give me 1 over 6 pi radians. For the 135 degrees, put it over 1 again. I'll put 360 degrees on bottom, 2 pi radians on top. Again, the degrees cancel out. I have 135 times 2 is 270. Still have the pi radians there, over 360. 270 over 360, both of those divide by 90. Give me 3/4. I still have the pi radians. Now, 1/6 pi radians and 3/4 pi radians, a lot of times will be written slightly different just to short it. 1/6 pi radians, they'll just put the pi up in the numerator of the fraction. So it's pi over 6 radians. And the same here, 3/4 pi radians, they'll put it as 3 pi over 4 radians. So they're just slipping the pi into the numerator of that fraction. They mean the same thing. 1/6 pi radians and pi over 6 radians mean exactly the same thing. Same with 3/4 pi radians and 3 pi over 4. So either one would be an acceptable answer. But if you look in the back of the book or anything for answers and it says one or the other, you know that yours is equivalent to it. So what if I give you something in radians? What if I say we have 5 pi over 6 radians, and I want to convert that into degrees? Well, this is already a fraction, so I don't need to do that. But what I am going to do is I'm going to put the pi and the radians in the numerator of that fraction and just keep the 6 down in the denominator. Technically, that's radians over 1, so putting it in the numerator is not a stretch. Now I'm going to multiply by a conversion factor, but this time I want radians on bottom so they'll cancel out, and degrees on top. So I have 2 pi radians equals 360 degrees. Now there's a couple of things that cancel out. The radians cancel out, and the pi's cancel out. So we have 5 times 360 degrees is 1800 degrees. 6 times 2 is 12, and now we still have to divide. 1800 divided by 12 is 150 degrees. So 5 pi over 6 radians is equivalent to 150 degrees. . Let's look at 7/8 pi radians. And we'll convert that into degrees. Actually, not 7/8. Let's look at 7/4 pi radians. I want to convert that into degrees. Well, again, the 7/4 pi radians is already a fraction. But I'm going to make sure I put the pi and the radians in the numerator of that fraction, like that. And now in my conversion factor, I'm getting rid of radians, so they go on bottom, going to degrees. 360 degrees on top, 2 pi radians on bottom. And once again, two things cancel out. The radians cancel out, but again, the pi also cancels out. So I have 7 times 360 degrees is what? 200 or 2,520 degrees. Over 4 times 2 is 8. 2,520 divided by 8 is what? 315 degrees, I believe. That's 315 degrees. It is very possible that we have an angle just listed as 2 radians.
Hey, Todd,
Yes,
on that last problem, where'd you get the 2 for the pi radians?
it's always 360 degrees equals 2 pi radians. That's
Oh,
our
yeah,
equivalency.
that's right.
Just like having 12 inches equals 1 foot. Good question, though. I'm glad you asked that, because some textbooks, instead of using 360 degrees equals 2 pi radians, they use, because you can divide both of those by 2, they use 180 degrees equals just pi radians. So it shortens the calculation a little bit, but to me, this one makes more sense because 360 degrees is a full circle, 2 pi radians is a full circle. So they both describe a full circle. But yeah, either way, if this is the one you were taught to use, that works as well. You just have to make sure this would be 180 instead of 360 if you change that to just pi radians.
Okay.
So what if we are given the angle is just 2 radians? There's no pi in it. There's nothing to cancel out. Well, we're still just going to put it over 1. We're going to have radians on bottom and degrees on top, so 360 degrees. It still equals 2 pi radians here. But all that can cancel out is the radians because there's no pi in our answer. So we've got 2 times 360 is 720 degrees. Over 1 times 2 pi is 2 pi. So to calculate this, we are going to have to actually divide it out. We're going to get a really ugly decimal answer. It's going to be 720 divided by 2 pi. Now, when we do this on the calculator, we have to be careful. 720 divided by, we have to do parentheses, 2 times pi. And then close the parentheses. Because we're dividing by both, we're doing the 2 times pi first, and then dividing by it. We have to have this parentheses to make sure that that's what we do. We get 114.59 degrees. So that 2 radians is an angle, converts to 114.59 degrees. I'm going to have you try a couple in your notes here. I'm going to have you convert 3 over 2 pi radians into degrees. And I'm going to have you convert 3 radians into degrees. We'll go over those in about a minute. Take a look at these. So our first one, 3/2 pi radians. But we're going to change it. We're going to put the pi and the radians in the numerator. So it's going to be 3 pi radians over 2. In our conversion factor, we're going to put radians on bottom. So it'll be 2 pi radians and 360 degrees on top. So the radians cancel out. And in this one, the pi's will cancel out as well. 3 times 360 is 1,080 degrees. 2 times 2 is 4. We can divide that, 1,080 divided by 4, 270 degrees. So 3 over 2 pi radians is 270 degrees. This other one is one that we just looked at, or similar to the one we just looked at, 3 radians. But we are still going to just put that over 1. And it is still going to be 2 pi radians on bottom, so the radians cancel, and 360 degrees on top. The radians will still cancel. We have 3 times 360 is 1,080 degrees again. And on bottom, 1 times 2 pi is 2 pi. So we have to do here 1,080 divided by 2 pi. So 1,080 divided by, now remember in parentheses, we have to do 2 times pi. And close our parentheses. Divides to be 171.89 degrees. This point is one of those days where you keep looking at the clock and the time keeps dragging, and I feel like I've talked a lot. We've covered enough material. I don't want to keep going because there's already going to be like 5 pages of homework. A reminder that there is a quiz out there from yesterday that you should be working on. So make sure you get that completed as you get a chance. There will be a new quiz out there for Thursday. That won't be due until next Monday, but it's coming up. If you want to, I'll get it posted later today. If you want to work ahead on it, feel free. And of course, we have our homework here. Homework today is out of the big book again. Page 572 to 576. Exercise 22-4. 7 through 21, the odd. Page 594 to 596. This is actually in the unit exercises. I'm just going to have you do 1 through 10. Page 610 through 611. Also in the unit exercises. Maybe look at 1 through 24 there. Page 614 through 615. Exercise 25-1. Maybe do 7 through 10 there. And the last page, page 619 through 622. Exercise 25-4. I'm going to have you do 7 through 23 of the odds there. So there's 5 pages. Most of these are just identifying some things, so they should go pretty quickly for you. With that, that's all we have for new material, so I'll let you guys have, we have about 25 minutes left here. I'll let you have that last 25 minutes to work on homework. I will be on the network to answer any questions if anything should come up. Otherwise, you guys have a great day.